Okay. Come. No, sorry, non dicevo. I was the to audience, come. Please. Okay. Let's start. So, in the last maybe 10 minutes, I will make a summary. But so far, no, the important result that we got was that the coupling of the gravitational wave. So there's not a good chemistry between me and the board, but can be written in terms of multiple. There is a lambda tensor that project out what is not transferred to the direction. So you see the same source. If you see in the same source, given a source as clearly in orientation, because it's a binary system, it clearly identifies a plane. If you see it from different angles, you will have a different waveform, okay? Because of the lambda tensor, because the lambda will project different parts of it into the gravitational wave. So, but this is, and then there will be corrections due to higher multiple, but we stopped here. Let's see how this affects the typical detector that is detecting gravitational waves. And then today I will give you some small hints, I mean, just a brief introduction of the data analysis. I mean, it's data analysis 101 that we do in LIGO or whoever is willing to analyze gravitational wave data. Okay, so this is the gravitational wave that arrives. You remember, it has a specifically simple form if it comes from the z direction. If it comes from the z direction, there are zeros here, 0, 0, 0. And then there is H plus, minus H plus, because the trace has to be 0. And then it's symmetric, so whatever is here must be also there. Okay? So this is when it propagates along the z direction. If it doesn't propagate in the z direction, well, it's straightforward. You put a rotation matrix here. If it propagates in a direction that is identified by two polar angles, you just rotate theta, you apply a rotation matrix with angle theta and angle alpha here and there, and then you see how it comes. So to see how it interacts with the detector, let's first work with the simplest case that is propagating along the z direction, and let's put the detector in the xy. So this is the typical detector we have to deal with. There is a laser. A laser is a source of coherent light. This is a beam splitter. I mean, who hasn't recognized this? That was a beam splitter. It's clear, right? And this is a beam splitter. The beam splitter, it's a semi-reflecting mirror. So basically, half of the signal goes 90 degrees, half of the signal goes through. So then there is a signal that goes into this arm. He hits the mirror at the end, and then another part of the signal goes into this arm, hits the mirror at the end, and it goes back. So it's important that the source of light is coherent, because you want to follow the phase. And basically, when the gravitational wave passes, it doesn't really change the position of the mirror. You know why? Because we always been working in the TT gauge so far. So in the TT gauge, if you want to compute the geodesics of the mirror, you have to do this. Okay, this is the geodesic equation for the position of the mirror. Okay, this is standard general relativity. And if you look at, for instance, the I direction, whatever space direction, then the mirror, of course, are almost static. No? Their velocity is absolutely not relativistic. So the only two components here for x dot that survive are x dot 0, x dot 0, and the gamma I 0, 0 is 0 in the TT gauge. So the effect of the gravitational wave on the position of the mirror is nothing. The mirror do not move under the effect of the gravitational waves. So how come there is an effect So you see there is the light, this light is coherent, so it carry on in space, this carry on in space, then it hits back in the beam splitter, and this is the photomultiplier. This is where light is recombined. And basically you have the two lights that are recombined need not to be in phase, so their combination will give some intensity of light that will have an interference. But what is important is that if this arm length is changed with respect to this arm length, the difference in phase will be slightly different for the two. And so the intensity of the recombined light will be different. We'll do the calculation explicitly. We'll see how the intensity of the recombined light depends linearly on the gravitational wave that is hit the detector. But then there is the big question. I mean, if the gravitational wave doesn't affect the motion of the mirror, I put them still, the gravitational wave arrives, they are still. How come that I see an effect? Well, because the propagation of light is, you have to put a geodesic equation. You have g mu dx nu equal to 0 will be something like this. Okay, and then this is g mu dx nu equal to 0. This is a light-like, was specified a light-like curve. You see, there is a perturbation in the metric, and so even if the coordinate of the path are fixed, the physical length is changed. Okay, so at the end, what you have to, let me go to the new page. Yes. So what you have is that for the first path, the light going from the beam splitter to the mirror, you will have that. For instance, let's think about the X arm. We put the two arms of the interferometer, one along the X-axis, one along the Y-axis, and the gravitational wave is coming from the both. So the time at which the laser get to the mirror minus the time the laser left the beam splitter must be given by the length of the mirror. Okay, will be the square root of the length of the mirror, and then the integral, then the square root, I just take 1/2. Okay, I'm just, okay.
You say the length of the mirror, you're not telling the distance from...
Yes. So I repeat the question in a second. As soon as I can go back to my previous slide. How do I go back to my previous slide? Anterior. It's written. Anterior. Okay. Okay. So the point is that the question was, no, I didn't want to cancel. Let's fazer. Yes. Okay. Okay. So the coordinate of the mirror is fixed. This is Lx and this is Ly. So we cannot assume that Lx and Ly are the same because these are kilometers, and the wavelength of this laser is a bit less than 0.1 micrometer. So the length of the tunnel in LIGO is not exactly the same 2 micrometer level. So, but the coordinate of the mirror is fixed. It's because of this. Because this tells me that x double dot is equal to 0, so the coordinate of the mirror is fixed. But what is not fixed is the physical distance, because the physical distance is not delta L, but is delta L integrated over Hij. And that's what I'm doing in the next. I'm integrating delta L. Okay, when I integrate, I get the 1, I get Lx, the size of the mirror. When I integrate there is an element. When I integrate the second piece, I get this. Basically, I have an effect that depends on the amplitude of the wave, because the amplitude of the wave modified the space-time in between, so this is not well. So basically, I have to integrate. I have to integrate the previous formula from an initial time, the time it left the beam splitter, to the time it reached the mirror. The time it reached the mirror, in principle, is T1, which depends on H0. But since this is already first order in H0, I can forget the dependence on T1 and H0. In first approximation, I can say that T1 is T0 plus L. Okay? But T1 is T0 plus L plus some H-dependent part, which is exactly computed here. But here I can forget the dependence of T1 on H0 just because this is already first order. So, and then I do the same for the, this is the path from the beam splitter to the mirror. So the mirror is really heavy, no? Because it doesn't have to recoil when the laser hits on it. And then there is the path from the mirror to the beam splitter, the path back. Then I have the T2. T2 is the time when it arrives back to the beam splitter. T1 is the time when it leaves from the mirror. T1 when it arrives at the mirror, and T0 when it left on the first time from the mirror. T2 minus T1 will be, again, the same thing. Plus 1/2. But now the integral is between T0 plus L and T0 plus 2L. Okay, did I answer your question, Susanna? Oh, okay. So you have you see the picture. I have my light. Light is leaving the beam splitter, goes to the mirror, and then comes back. Comes back at the time T2. The time T2 it comes back, then he meets his old friend, no? The light that was was separated from him at birth, but then he came back from the other mirror. So, by definition, what we see is the light that arrives at the same time. We see the recombined light that arrives at the same T2. But it could have a different T1 and a different T0. So basically, the difference in the phase of the recombined light is due to the fact that they arrived at the same T2, but they left the beam splitter at a different T0. Why? Because the X is actually sensitive to what? To HXX. Okay? This is HXX. Whereas the Y arm is sensitive to HYY. And you remember, for a gravitational wave coming exactly from the Z direction, HYY is exactly minus HXX. Okay? So I have an effect with the plus on the X arm, and effect with the minus, exactly the same effect with the minus on the Y direction. So let's now take some simplification now. Let's assume that the waveform is just cosinus of omega GWT. It's just a constant time cosinus omega GWT, so the integral, I can do it analytically very simply. And so look at here what happens. It happens that the recombined light, for instance, the electric field that arrive at the beam splitter at the time 2, and the travel in the X direction, it carried the phase that he had at the beginning. No? We have to follow. No, we are living on the crest of the wave. No? We stay on the crest of the wave at T0. We hit the mirror at T1. Then we go back the beam splitter and T2. And this is the T0. This is the phase that we carry over our trip. And we just express T0 from T2. No? We add these two equations. So we add this to this. And so we get that this will be e to the omega LT2, and then there will be an effect. T2 minus, I get this minus this, you get minus 2Lx plus 2Lx. No, I get, sorry, yes, T0, well, this is T2 minus T0. I bring T0 on the other side and Lx to the other side, so I get minus 2Lx. And then I get the factor that is dependent on the gravitational wave. This factor is dependent on the gravitational wave. It's in the exponent, but H0 is always very small. It's 10 to the minus 20. So let's put it down. When we put it down from the exponent, we'll give you 1 plus H. The piece that doesn't depend on H, we forget it. We just only want the piece that depends on H. And then we get H0. Yes. We have to do the integral, and to be careful, this would give me a sinus of omega t0 plus L minus sinus t0. This will give me sinus of, this is t0 plus 2L, of t0 plus 2L minus a sinus of t0 minus L. So this extrema cancel with this extrema, and then I get, let me make some space. And then I get sinus of t0 plus 2 omega GWL minus, sorry, I have to go in the line below, t0, if I did things right. Exactly, no, I was right. And this was the integral. Once I integrate, I 1 over omega GW. Because this was the cosinus, I integrated sinus divided by omega. Okay? Then this is the electric field of the laser that travels through the x-axis when it goes back to PST2. I do the same for the laser wave that travel through the x-axis, through the y-axis. So, and it's exactly the same, except that now H0 is a minus, because you remember, HXX and HYY is exactly minus HXX. So when I combine things together, the laser, yes, because the pagina anterior, yes. Of course, what is the behavior of the electric field of the laser? I mean, of course, here there is an E0, no? There is a constant. This is the amplitude of, who was asking the question? Yes, the question is about omega L. Here there is the amplitude of the electric field of the laser. That doesn't care, we keep it constant. And omega L is the angular frequency of the laser, of course. The electric field is oscillating with some frequency. And so when we recombine everything together, so at the photodetector, the electric field at the photodetector will be the electric field that travel on the x-axis plus the electric field that travel on the y-axis. Of course, will be the sum of the two. And when we sum the two, the part that is not H0 dependent, I mean, is constant, so it doesn't vary with time. The part which is not dependent will be basically, well, yes, what we have, we'll have. Let's do things right. We'll have an amplitude that is always there, and it doesn't care. Then we'll have a factor that is e to the e minus omega laser T2, that will be the same for the two, because by definition I'm looking at the light that recombines. And then here I put 2L, where by L I define the average between LXY and the LX and LY. And then I get, sorry, here there is something that I need to use. So this is a trigonometric identity of alpha plus 2 beta is equal to sine of alpha plus cosinus plus twice cosinus of alpha plus beta times sin beta. Okay, this is just a trigonometric identity. It's an identity. If you can read it, you probably can't. Let me write it a little bit better. This is sinus of alpha plus beta is sinus alpha plus twice cosinus alpha plus beta times sin beta. I mean, it's not trivial, but it's an identity. Why I want to use that? Because look at this. Here I have the subtraction of this. This is alpha plus 2 beta. Okay, sorry, here there is an omega laser that was missing. No, omega GW. Yes, I put omega GW just in front of L, not in front of T, sorry. So this is sinus of omega GW, T0 plus 2L. And this is GW. It just came out of the integral, no? Because the physical finite length is just the integral of g mu the x, the x. So I just do the integral, I get 1 over omega, and then omega t plus 2L minus sinus. After I use that identity, you see, I trade this for something which is omega t plus omega 2L. I traded for omega t that canceled the other one, and then I'm left with this. And so, at the end of the day, I'm left with this piece, which is a common factor between the two. And then let me rewrite times. So this should be here. Then for this is a common factor for the two. Then for the part from the EX, it has the following piece. The part from the EX it has the following piece: omega L Lx minus Ly divided by 2. You see, because no, not divided by 2. Because here I had Lx plus Ly, but the piece of the field, the travel over x, it had to be only Lx. So I put minus Ly to compensate this. And then it had its piece proportional to H naught. And this piece proportional to H naught is H naught omega L, because H naught was in the exponent, but I developed because H naught is very small, omega GW. The omega GW in the denominator came from the integral of the cosine, gave me omega GW in the denominator. The omega L was in the exponent, I expanded. And then there is this piece, sinus of omega GW L, this piece. And then there is times, I don't have space. How do I create space? So this formula is just a trigonometric formula. Let's cancel it because I need the space. Okay, and then I get the rest of the piece, which is the cosinus of omega T2 minus L. This is GW. Okay, so this is just the, okay, so this is only the piece from the X. Then I have to add the piece from the Y. The piece from the Y, the field that I'm propagating into the Y arm. Well, look at this. This is exactly minus, because this has to combine this piece I'm putting in evidence. This is the times. So here for the Y-axis, I had omega laser T2 minus 2Ly. So I take this and I put it there. And then I have exactly the same effect, but with a minus. Okay, I don't need to copy it. For the y-axis, it's exactly the same effect because the wave is coming from the z direction, so we know that hxx is exactly minus hyy. So look at this. This is exactly the combination that give you the sinus of this. So I can put in evidence this knot, and this is the combination that that exactly gives you the sign, because it's something. Okay, here we can actually we didn't need to develop at this level. We could have left it on the exponent. So we get e to the I something plus something minus e to the minus that something. So this is exactly then the sinus. So this is exactly the sinus of delta phi, where delta phi is this piece. Is this piece that does not is omega laser L x minus Ly, but I mean we don't care. It's just a number. It doesn't depend on time. Phi 0 is exactly what we need. Give us the dependence on the gravitational wave. Sorry, in the notes is the other way. Phi 0 is this one, and this is the delta phi that depends on h. Phi 0 is the constant, and the delta phi that depends on h is h0, the amplitude of the gravitational wave, omega laser, that was there from the beginning, the phase is always modulated by the omega laser, 1 over omega gravitational wave that came out of the integral, and then there is this effect sinus of omega gravitational wave times L, this one, and then there is the standard modulation cosinus of omega gravitational wave t. So this is the original gravitational wave that gives a modulation to the sum of the two electric field. And this is the non-trivial factor. You see the combination omega laser, omega gravitational wave times sinus of omega gravitational wave times L. Okay. So what is important to remember, the computation, I mean, it's not difficult. It's just adding to fields. Just adding to exponential, recognizing that at the exponent here I have something, and here I have exactly minus something. So when I add the two, I get the sinus of the exponent. So at the end of the day, I have a result that exactly follows the time behavior of the wave, plus a modulation that depends on the size of my arm. Okay, the omega of the laser is what it is, the omega of the gravitational wave is just a multiplicative factor, but now we can play with the size of the arm. What is the typical L that will give me a better amplitude? So the L that gives me a better response of my detector must be pi divided by omega gravitational wave. Clearly. So pi divided by 2, sorry. There is it. I mean, this is a sinus. So the best response of the detector to the amplitude of the gravitational wave is that when L is pi divided by 2 omega gravitational wave. Let's put in the number. So if we put our detector answer well to 100 Hertz, say, if we put here 100 Hertz, pi divided by 2 is of the order 1.5. And 100 Hertz we have to convert to kilometer. What do we do? So Hertz is like second to the minus 1. So we take out Hertz here, and we put second here. Then we multiply by 3 to the 10 to the 5 meter per second. Second and second simplify. And this gives something of the order of 5 times 10 to the 3 kilometer. So it's very good. We just need to build a detector whose arm are 1,000 kilometers and will be very sensitive to gravitational waves. Do you think we can do this, build a detector with arms of 1,000 kilometers? That's pretty hard, no? Indeed, LIGO has only 4 kilometer arms. Virgo has 3 kilometer arms. So that means that if you trust this formula, they have reduced sensitivity, because then if L is so small, then basically you get that instead of the sinus, you can approximate with the argument, and so you get a sensitivity which is proportional to L for small l. So why didn't they build it longer? Well, of course, the longer the better, because you would have more sensitivity, at least in the regime in which the sinus is linear. Then if you exceed the region where the argument of the sinus is pi over 2, you don't gain any more, but we see that it's a long way to get to that distance. So there is the experimental trick. The experimental trick is to put mirrors. Yeah, the experimental trick, the light doesn't go back and forth once, but there are mirrors that basically make the light goes back and forth several hundred times. And so the actual optical path of the photons is of the order of 1,000 kilometers, or few hundred kilometers. But the arm needs physically to be only a few kilometers. Okay, so you have few kilometer arms, but the photon goes back and forth few hundred times, and so in practice you have like amplified the mirror by this factor. Then you see you must not have too many bounces, because you have too many bounces, then this effective L exceed this critical value, and then you start losing, because this is a sine, it's not linear. But as long as omega L is sufficiently small, this is always increasing, okay? So this is the basic, I mean, it's much more complicated than this, but this is the basic of the interaction of the gravitational wave with the interferometer. The gravitational wave arrives, it stretches one arm, it squeezes the other arm. It doesn't really move the detector in this gauge. Of course, you can work in another gauge in which the mirror moves and the space-time in between doesn't stretch and squeeze. But this is just an artifact of the gauge. What is not an artifact of the gauge is the amplitude of the electric field of the recombined light. The amplitude of the electric field of the recombined light that we computed in the TT gauge, it doesn't change if you compute in another gauge. And it has this dependence on the amplitude of the gravitational wave. It follows the time behavior of the gravitational wave, and its amplitude is modulated by this factor, and so you need to adjust the length of your detector, or to artificially adjust the length of your detector to maximize the response to the gravitational wave. And then, okay, this was for a wave coming from above. What happens is the wave coming from an arbitrary direction? Well, new page. What you have to do is that the same computation, we keep the detector in the xy plane. So we are always sensitive to hxx and hyy. But what we have to do is to take the original waveform, you have to take the original metric perturbation and apply a double rotation. You apply, if you want to consider the case, I mean, this is again the detector with the mirror here, the mirror there, the laser here, the beam splitter, and the photodetector. So if the wave is not coming from here, but is coming from a direction identified by two polar angles, let's say alpha and beta, and beta, these are the two polar angles, what you do? You apply a rotation around the y-axis of beta, and rotation around the z-axis of alpha. First the rotation around the z-axis of alpha. Then rotation around the y-axis of beta, rotation around the z-axis of alpha, and here the same rotation to the -1. No, this is the standard way you rotate a tensor in 3 dimensions, and so you obtain a new hxx and a new hyy, okay? And what happens is that then the output of the detector that we have computed was proportional to hxx, say, because hyy was minus hxx, so we could, that h0 that we wrote was actually xx, or we better call it h plus. So when the wave is coming exactly from the z direction, is only proportional to h plus. This is output, is not a zero. Output of the detector will become proportional to h plus times a factor that depends on alpha and beta, plus it will also depend on h cross plus another factor that depends on alpha and beta. Okay? It's straightforward to do. You just put the matrix here, you rotate, and you go and check what are these two elements in the new rotated matrix, no? Because the detector, I kept it in the xy plane, so it keeps responding only to hxx and hyy. Okay? So in particular, hxy cannot affect the detector by symmetry, no? hxy never affect the detector because this polarization affects symmetrically the axis x and y, and our interferometer only measures differences between x and y. So the actual form of these two functions, I mean, just to the rotation, is this one. This for f plus, and f cross is equal to cosinus beta sinus of 2 alpha. Okay, so sinus of beta, sorry. Did I remember that right? I hope so. No, was a cosinus. Why? Okay, so the no, I think it's wrong in the notes. It must be a sinus. Beta goes to pi over 2. No, it's okay. So, whoa. Okay, so the important thing is that basically, so if the wave comes from the z-axis, so you only feel h. There, it must be a sign. It must be a sign, no? Because when beta is equal to 0, when beta is equal to 0, it must go to 0. Okay, so okay, I will check that in the notes. Yeah, you're probably right. Okay, I will check this. I'm a bit confused now, I must admit. So this is written in the notes. Yes. Ah, no, you're right. Yes. You're right. It's a cosinus. So when beta is equal to 0, you can take alpha equal to 0, and so you don't have a reaction to F cross. You only react to H plus. When then you see as you decrease the angle, then the projection of what actually affects your detector become less and less, but is never 0. You see, even when beta is pi over 2, the F plus response is minimal, but is not 0. When beta becomes pi over 2, you have 0 response to F cross. You only have 0 response to both of the polarization for this kind of incident direction. Beta equal to 0 and alpha equal to pi over 4. Okay? For this kind of incidence wave, you get 0 response of the detector, absolutely 0. Well, why? Because a wave that is coming here sees the detector exactly in a symmetric way. No? The detector is in the plane, is like this, and the wave is coming at 45 degrees there, in the plane of the detector. This is the only way we are completely unsensitive to. And actually, not only this, but all the 4 directions in the plane. So if you look at the response of the detector to something that arrives from the sky, an interferometer will always have 4 blind spots. The 4 blind spots correspond to the 45 degrees direction, to the 4 45 degrees direction that are in the plane of the detector. Okay, these 4 45 degrees direction, they give you 0 response, both for plus and both in cross polarization. Whereas all other direction, they give you some slight modulation, but they don't give you 0. They might give you 0 from some specific angle, but just on one of the 2 polarization. Okay. So this 45 degrees always kill the F cross, but never kills. 45 degrees always kill the H plus, but never kill the H cross unless you are at beta equal pi over 2. Yes. No, it is a cosine. I don't see why. The cosinus of beta? Yes, but this is a problem with the polar coordinates. It's not a problem of the math. You see, the polar coordinates are degenerate. No? You don't need alpha and beta to determine the North Pole. So when beta is equal to 0, the response to F plus and F cross is exactly the same as it should be, because you can just alpha and beta. I mean, alpha is a redundant angle. You only need beta equal to 0. So this formula doesn't actually apply exactly beta equal to 0. Just because polar coordinates do not make sense at exactly beta equal to 0, because alpha is meaningless at beta equal to 0.
If the wave was linearly polarized, then you...
So the point is that if the wave comes from here and it has no hxx, so if the wave comes exactly from the z direction and it has 0 hxx, xx, and it has only some hxy, it has only x cross, right, we don't see it. The point is that this formula exactly for beta equal to 0 you cannot trust because alpha is meaningless for exactly beta equal to 0. But this is the problem of polar coordinates. It's always the problem. No? There is one point. Otherwise, the sphere would be R2, but it's a sphere. It's not R2 because it cannot be covered with a single map. Okay. So this is to tell you that this kind of interferometer always have some blind spot in the sky, which correspond to this 445 degrees direction in the plane of the interferometer. And the top response is from when things come from above. When things come from above, it has the top response because this is equal to 1 and this is equal to 1. That's always the best. Then they start losing. You see, here basically if the things come from the plane of the detector, they see only 1/4 of the signal because they see 1/2 in the plus polarization and 0 in the cross polarization. And then if the signal comes from below, then they start again, and the gain is maximal, but it's again maximal if things come from below. So maximum, minimum but not 0, and then maximum again. And then there is a modulation with the direction in the plane of the detector that gives you, they can send it to 0, the total response, when the signal arises from the plane of the detector in a symmetric way between the two arms. Question on this? And then otherwise I slightly change topic slightly. Sorry? Well, just statistically, since we don't work at super high signal to noise ratio, if you see, you can lose up to 1/4 of the signal to noise ratio if you are from very good to not very good sensitivity. Since the highest signal to noise ratio that we got was 30-ish, you see, you divide 32 by 4, you already fall to 8, which is a kind of a threshold. So yes, most of our detection, they happen to be confined in the best region. But it just I mean, if you could detect things at signal to noise ratio 1,000, we wouldn't care, no? Because even 1/4 of 1,000 is still very visible. But since we detect things around 30-ish, 20-ish, then of course, yes, we have few detection from this direction, and most of the detection are from here. This is just a selection effect, and we cannot do much about it. What we can do is we can add detector oriented differently. So what is blind for this detector is not blind for the other. So the two LIGO are oriented in a way that the blind direction are the same for the two LIGO, but this is because you want to have a double coincidence, because you don't want to have a signal in one detector and 0 signal in the other because it happened to be in the blind direction of the other. That would be a problem, because maybe it was a real signal, but maybe not, because maybe it was just a statistical noise fluctuation. So you want the first two detectors you have, you want to have a line in the same way, so they see with the same modulation. So if you see one, you must see the other, so you have confidence. Then when you start adding 3, 4, 5 detectors, it's better to have different orientation, so you start seeing the things that the first two might have missed. Yeah, Virgo is oriented differently also because it's very far away, so it would have been impossible to orient in the same way putting on the surface of the Earth. Clearly, you know, there is the curvature of the Earth that even the two LIGO are not perfectly oriented just because they are 3,000 kilometers apart, and so they are not exactly in the same plane. They are kind of similar plane, but not exactly. Okay. So, and then, by the way, when the wave when you're relating two frames, you usually should think about 3 angles. No, there are 3 other angles that relate one frame, like the frame of the arrival of the wave, to the frame of the detector. There is a third angle that affects the response of the detector, which is the polarization angle, that is usually indicated with psi, that it denotes rotation in the plane orthogonal to the direction of propagation. So the psi angle exactly mixes the two polarization. So it embodies these degrees of freedom that it's a rotation in the direction of propagation, so it mixes H plus and H cross. And so psi is the third Euler angle that relates the frame of the incident wave to the frame of the detector. So you need 2 angles to determine the direction, and the third angle to completely fix the third order angle to completely fix the frame. Shall I move on? Okay. Nice one. No, yeah. Okay. I forgot what I wanted to say. Ah, yes. Just to go back, remember, here there is the detector. Now we make the detector as a point. Okay, but it is actually a triad. Here there is the direction of propagation, and here there is the binary. So the orientation of the binary is still identify another axis. This axis has nothing to do with the direction of propagation and nothing to do with the axis of the detector. Okay, so this other axis, if you want to know how Hij depends on the orientation of the binary, that's the 2 angles in the projector that enters. Okay, here you have n, the direction of propagation, and n is embodied here. So this has to do with the polarization. Then the projection of the polarization onto the detector depends on those 2 pattern functions that we just computed in the previous slide. But now there is a Hij dependence on the relative orientation of the binary with respect to the propagation direction. But again, we use the same trick. We say that if the binary is oriented such that the propagation of the wave is along the z-axis, it's trivial. We have, let me write bigger, otherwise I make a mess. So we have qxx minus qyy divided by 2, qxy, qyx, and minus the previous one. Okay. This is the quadruple tensor if I put my source in the xy plane. And then if I look at it from the z plane, I don't have, from the z direction, I don't have to project out anything. But if I look from a generic direction, the best way is to rotate by an angle iota. Oops, why did it do that? I rotate, so this is the n, this is minus n. No, this was the direction of propagation. I prolong the vector here, and this is the angular momentum of the binary. So the vector perpendicular to the plane of the binary is angular momentum, and this is iota. Is the inclination between the angular momentum of the binary and the direction of propagation. Since this is my quadruple tensor that fits the gravitational wave in the frame where the binary is in the xy plane, if I want to put it in a generic inclination, I have to rotate. And as before, I rotate. Okay? And so I obtain a new formula for the quadruple, in which if I keep the direction of propagating in the z-axis, because now I have my quadruple in a generic plane, then I cut in the result of this all the z components, and then I get for free the quadruple component that feeds a plus and a cross. And if you do this rotation, you see that H plus respond to cosinus quadro iota divided by 2, and H cross respond to cosinus iota. I mean, you just have to do this rotation. It's trivial. Just do the 3 by 3 matrix, you apply it, and you see that you obtain a new matrix, and in the XX part and in the YY part, you get this times the old plus polarization, and in the XY part of this rotated matrix, you obtain the old, what was there in the old XY piece, but now modulated by cosinus of iota. Okay, so you see there are a lot of angles involved in general in gravitational propagation and detection. Here you have the alpha, beta of the location of the source with respect to you. This is us. We are sitting next to the detector, and we look at the source with some angle alpha and beta. Then you have psi, which is the angle that tells you how I can shift between H plus and H cross by making a rotation around the z-axis. And then I have this iota that tells me the inclination of the binary with respect to observing direction. And then I have a final angle phi that tells me how I rotate inside the plane of the binary. It doesn't affect iota. Okay. So this is to tell you that at the end, what I'm sensitive to depends on these angles. And just to make a summary, if I want to make the detection of my gravitational wave, then we'll have a iota dependence due to the inclination of the binary with respect to the angle. Then my location in the sky, psi, and then phi, which is this additional angle that rotates in the plane of the binary. So this has to do with the orientation of the binary. This has to do with the location in the sky. And this is the polarization that tells, we have to measure them because they affect the amplitude of the gravitational wave in the way that I told you. These ones enter the pattern function. And these two enters the polarizations. See? So in particular, these two, they don't know anything about us. No? They only have to do between the direction of propagation and the direction of propagation orientation with respect to the plane of the binary. So they are intrinsic of the binary with respect to the direction of propagation. These ones depends on the detector. So a detector in the US, a detector in Italy, a detector in Japan will see this angle differently because the location in the sky, the detector will be, also, I mean, on the surface of the Earth will be this kind of differently. Okay. So the next thing I want to do is to make an analytic computation of how much time do we have? 10 minutes? 50, no, 20?
5 minutes.
5, okay. What I want to show you, okay. I want to show you how to do.
20.
Okay, so 20. I want to show you how to, okay, remember, no? We have H plus and H cross. In H plus, we have 1 plus cosine squared iota over 2. And then we have the factor that depends on the quadrupole. And then we have some cosinus of phi. Okay, this is the typical structure of the waveform. So you see, this is the quadrupole with two derivatives. The quadrupole with two derivatives, no, the quadrupole is the second moment of the mass, is mxx. Once I take two derivatives, I get two velocities. So it's the kinetic energy, 1 over the distance, because of course the amplitude of the wave goes with the distance. And I have, actually, is the mass ratio, is the reduced mass, no, that enters the quadrupole. And I like to write the reduced mass as the symmetric mass ratio times the total mass. Remember, the symmetric mass ratio was, so symmetric mass ratio times m is the reduced mass. Okay, so this is the kinetic energy divided by the distance, and then there is the phi that tells you how the waveform is moving around. Okay, and this will be sinus. Then when you see, you don't actually measure H plus and H cross, but each detector measures a linear combination of H plus and H cross. Actually, I told you now, the answer of the detector to the gravitational wave is not linear, but of course H is so small that you expand to linear level, and that's more than enough. Okay, so the detector will see a linear combination of these two, where the coefficient in front will be those pattern functions that depends on where on sky your detector see the source. So at the end of the day, we have to correlate with we have to look into the data and check if there is a signal. So since the signal is very small, the thing to do will be the following. We take the output of the detector, that will be hopefully signal plus noise, and we say, look, since the noise, as I sketched the other time, will be something like this with components of noise at all frequencies, and the signal will be something much nicer and well behaved, but much smaller. And actually, this is highly exaggerated because the signal is several orders of magnitude. It's not a factor of 10, it's a factor of 1. Sorry, the noise is few orders of magnitude larger. What you want to do is to correlate this output with some filter. And we do in Fourier space, and we say that we want to take a filter of this. You want to filter the output by integrating my signal plus noise with some filter function. Okay, in time domain of Fourier space, I mean, in principle, is the same thing. Okay, I mean, it's not the same thing, it's equivalent. So this is my filter function, and then of course my filter function I want to shift it with time. So, I mean, I have my output, I have some filter function that might have some profile, and I want to slide around the profile of my filter function, and in Fourier space it's trivial to slide in time a function. You just multiply by e to the pi f t0. So let's forget about this because anyway, we just want to sketch the idea. So this filter function can be easily shifted in time just by multiplying by this factor. And we want to see what is the optimal filter function to get the filtering. So first there is one problem. If whatever optimal filter function we might find, if we take it something linear, the output of the filter will depend on the normalization of the filter function. And that we don't like, because how do we choose the normalization of the filter function? If we choose a filter function that is once or twice or thrice, the output will change. So we better put in the denominator something that kills this dependence. And actually, instead of the filter function, what we want to do is a sort of signal to noise ratio. So we want to put at the bottom just noise time filter. And at the numerator, we want to put just signal. Okay, the idea is that the output of the detector cannot separate signal and noise, no? Otherwise, we wouldn't need a filter. That's what we want to do. So separate by n signal plus noise, it's impossible. No? The output of the detector contains everything, contains all this mess. So if we take but we want to enhance all the signal, not the noise. So the idea is that, but the noise is sort of random, whereas the filter, it imprints the shape of the signal. So the idea is that, suppose we have a filter, we haven't found it yet, but suppose we have a filter whose correlation with the noise is 0. Then it's okay to drop this, so this is the output. Putting here either the output of the detector or just the signal is the same thing, because we have postulated that this filter has 0 correlation with the noise. This is a reasonably good assumption, no? Just because the noise is changing wildly, whereas the filter will have the shape of the signal. But then look at this, then it doesn't work in the denominator, because if I pick the filter to have 0 correlation with the noise, this cannot do. Okay? So what I have to do is to do this. The correlation of the filter with the square of the noise. And then took the 1/2. So if I take this, then I have a filter that if I tune it well, it correlates well with the signal, it kills the noise, but then if I want to measure signal over noise, at the denominator I have to put the square of the noise square of the signal, because otherwise filter times noise would give 0 correlation. So in order to do this, there is a standard way to do this, which is instead of taking one chunk of data, measuring the Fourier transform of the output of the detector. After all, if you take the output of the detector, that's all noise, no? Because the signal is very tiny contribution. So it's all noise when you correlate with itself, but it's all signal when you correlate with the field. So the idea is that we characterize the detector with this function. We take the output of the detector, we take the Fourier transform, and we say that we take this, and we average over many realizations. For example, we take 1 hour of data. We take, I mean, the output of the detector, as I show you, is the intensity of the electric field, so it's a number for every instant of time. So it's a time series. So I take the Fourier transform. I can put And this here I call it noise, but it's actually the full output of the detector because the signal is so low that I can take the full output of the detector. Then I take the Fourier transform over a chunk of 1 hour of data, I multiply by this, and then I throw away, I take 100 hour of data, I take 100 hour, I do this 100 times, and then I divide by 100, of course, because I want to take the average. Now, there is a fundamental property that this output will be proportional to a delta function between f and f prime. This is because I expect this noise to be completely uncorrelated at different frequencies. So this noise will be amplitude and phase. So the phase for each pair of frequency will be arbitrary. And if I take many realizations, like 100, 200, 300, the sum will completely cancel all the correlation. But when f is equal to f prime, when f is equal to minus f prime, when f is equal to minus f prime, this is the star of that. So this is modulo square. So even if I take the average, it cannot go to 0 because it's always positive. And so whatever comes out of this average, I call it 1/2. I mean, the 1/2 is conventional, the spectral noise density of my detector. There is one caveat here that is often overlooked. So things are not done in continuous space, no? Because what you do, you have a sampling of the data like every, I don't know, millisecond, tens of milliseconds. So the Fourier transform is a discrete one, it's not a continuous one. You don't integrating over time from minus infinity to infinity. So this is in discrete space, this is usually replaced by a delta of the two frequencies, which are discrete, and 1 over delta f to save the dimensions. And you can understand that this is the right thing, because look at this. When you take the Fourier transform of 1 hour of data, and if you take the Fourier transform of 2 hours of data, you expect the amplitude of the Fourier transform to be the same? No, because the Fourier transform is a sum weighted by some exponential, but it's the sum of your points. If you take twice as many points, the amplitude of the Fourier transform will come out differently. Okay, and so the Fourier transform of the output of the detector, Fourier transform of the noise, is not a good indicator of the performance of your detector because it depends on the length of your sample. Okay, but the spectral noise density is, because the spectral noise density, it's what comes out of this that depends on the length of the sample, but multiplied by 1 over delta f. And this 1 over delta f is exactly what normalizes the result to something that is independent on the length of the chunk of the amount of data that you use to estimate your noise. Okay, as you can see, as you increase the time over which you take the Fourier transform, the Fourier transform grows as the square root of the number of samples. So the Fourier transform square grows as the number of samples. 1 over delta f is exactly 1 over the number of samples. It's 1 over delta f is 1 over the time over which you take the Fourier transform. So this is also grows with the number of samples. And so this gives you the spectral noise density as the real quantity to monitor the performance of your detector. So the performance of your detector is not the Fourier transform of the output, but is this object that you take after doing many average of many realization of the noise and observing that you have a delta when the two frequencies are not the same, and then you obtain this function. So when we plug back this here, then we get when we plug back this here, we get integral over df, integral over df prime, 1/2, let me forget. Okay, let's go to another page. So in the denominator, we had df prime, we had the noise, but then noise, we replace it with this. And then we have the modulo square of the filter function. At the numerator, you have the signal times the filter function. Okay, then because of this property of the noise, then we can get rid of this. And so you see, and there was a 1/2. So at the end, we have arrived to our estimator of the signal to noise, which has all the good properties. It doesn't depend on the normalization of the filter. No? If I multiply the filter by any number, it drops out. It's linear in the signal, and it's linear in the noise. Because if I multiply the noise by 2, the spectral noise multiplied by 4, but I have the square root. Okay. Linear in the signal, I mean linear in the inverse of the noise, of course, I mean linear in the denominator of the noise, and independent of the filter. So now we just have to find what is the best filter. So this is solved very elegantly. Yes, questions? Okay, yes, it's the Fourier transform of the filter, yes. Yes. So here, and this is the spectral noise density. This is a nice, this problem is a nice solution in terms of scalar products. So what is the K that maximizes this output? Well, if we define a scalar product between two functions like this, so this is my definition of the scalar product. Then you say, what is my choice of B that that maximize the scalar product of B with A? Well, no, it's two vector when their scalar product is maximum. Okay, if I rescale B by an arbitrary amount, of course I can increase at will this product. But I mean, suppose that B has a fixed norm. What is the choice of B that maximize the scalar product with A? When the two are parallel, no? I just choose B to be parallel to A, and I'm sure that for a given norm, this is the maximum I can obtain. There's no way to go beyond that. So if we manage to write this as a scalar product, we are fine. And indeed, this is possible. It is possible to write the SNR as a scalar product. We just had to write oh, yes, this, I just have to write now, pen, SNR, the one I wrote before, it just happened to be equal to my scalar product of my signal with the unknown function that I have to write, that I have to find, divided by the norm of this unknown function. No? I want to divide by the norm because I don't want my output to be dependent of the arbitrary normalization of my filter function. And look at this. Given the definition above, this would be h times u star divided by Sn, integral over df, divided by u times u divided by Sn. Okay, this is just the definition of the scalar product I gave earlier. So this follows from the definition. Now I'm telling you that the SNR that I wrote above can be written like this. Yes, it's enough that I choose u is equal to k times s. If I choose u equal to k times s, here s and s simplifies, I get hk. Here I get KKSN, and this is exactly what was here. I get KKSN and SK. So the solution to this maximization, once I recast the problem in this mathematical language as a scalar product, is trivial. I just need to write U to be K times Sn. Or if you like, K is equal to, I put it on the other side. So if I take the signal to noise ratio is H times, no, it was better the other way. Okay, so my signal to noise ratio will become H times H divided by Sn, integrating in the F to the 1/2. There is some prefactor that I forgot, but this is the result. No? You just plug in. No? You must have U equal to H, but U equal to H is the solution of the maximization of the scalar product. U equal to H gives you K K is equal to H divided by Sn. So in the original signal to noise ratio, I had H times K, but K is equal to H divided by Sn. So this is my signal to noise ratio, and in the denominator, I also get H squared divided by Sn. And so this gives me overall HH divided by Sn. Sorry, this was to the 1/2. To the 1/2. So this is the formula for the optimal filter. So if I want to take the output of the detector and filter, so to dig up yes. Okay, sorry here. I get to the good point to stop. Yes, because I guess we're getting hungry. So the last thing in 2 minutes I want to show you is that okay. The last thing I want to show you is that if you want then to get a good model of a H, this is my H. So the filter, so we found that the filter is local in the Fourier space. The filter basically is H divided by noise. Okay. So what we have to do is we correlate in Fourier space the output of the detector with a filter that is not exactly the H which is hidden in the output of the detector, but is H normalized by noise. And by the way, what you get usually is in the picture is the spectral noise density, because as I demonstrated, this is the meaningful thing to quantify the performance of your detector. Is the spectral noise density as a function of the frequency. So, and if you look well in the plot, the units of the spectral noise density is Hertz to the minus 1/2. Why these funny units? Well, you remember, as a matter of units, Sn was kind n tilde square, Sn times a delta over frequency. A delta, n is the Fourier transform of the output of the detector, which is dimensionless, so this is time square. This is the delta, is the inverse of the frequency, which is time. So, yes. So the spectral noise density must have dimension of time. So, and when you look at the spectral noise density, basically you have to compare the square root of the spectral noise density to the intensity of the waveform. Then you plot the square root of the spectral noise density, which must have dimension of square root of time. That's why people usually plotted this inverse square root of Hertz, which is the same as square root of time. So this is the thing that people plot, the square root of the spectral noise density, which has units of inverse square root, which units of square root of time, also inverse square root of frequency. And then on the top of it, you see the plot of this waveform, or the amplitude of the waveform. The waveform has a computable slope of f to the minus 7.6. So in the 1 minute left, I will sketch how you get to this f to the minus 7.6, which is analytic. But am I consuming the question time, or there is still time for question? 0 minute plus question. I consumed it. Sorry for that. Then I stop. I didn't mean to consume question time. So just 30 seconds, just to tell you that when you do the Fourier transform, when you do the Fourier transform, to get, you remember, we had so if I have my waveform, I have to do the Fourier transform to get H tilde. What I get is that you might think that since the velocity of the binary is pi gm f to the 1/3, f gravitational wave to the 1/3. This I show you in the first in the first lecture, you might think that a higher frequency, you get higher power, no? Just because the amplitude of the waveform in time domain goes up as the two object approaches, no? When the velocity of the binary increases. So the two objects, they tend to merge, velocity get close to 1, and so the frequency and the velocity increase. So in the Fourier transform, you get that this piece of the waveform contributes to this frequency, this piece of the waveform contributes to this frequency, but here the frequency is changing very rapidly. Here the frequency is changing very slowly. So what happens is that there is a dependence like v squared, so higher frequency has a higher amplitude, but then there is a dependence on how many cycles the waveform spends in that frequency. And that is proportional to the square root of f dot. This is one of the exercises. So f dot, you remember we computed was, we computed t dot, but f dot, so v square is f to the 2/3, f dot to the 1/2 is f to the -3, and so over, no, not to the -3, so at the end you get f to the -7/6, because you have to put here the right coefficient, which I cannot guess in a hurry, but it just comes from f dot that we computed at the time, and then here you get f dot, 11/6, yes. F dot was 11/3, we computed earlier. Inside the square root gives you 11/6. When you combine the two things together, you see that the slope of the gravitational wave in Fourier space goes as -7/6. Sorry for being over time. Stop.
Thank you, Ricardo. Any questions?
Yes. Yes, you see, I mean, from the very beginning, I told you that there are these two functions that you need to know. So, E and E dot. Okay, so the combination of the two gives you the t dot or f dot over f that goes as m chirp f to the 11/3, m chirp to the 5/3, and some coefficient. Okay, so when you short circuit these two functions to compute the phase, you remember, no, the first time. The first parameter that matters is this m chirp. Okay, the first parameter that affects more the construction of the phase. Then there are all the parameters entering here in these post-Newtonian corrections, and these are basically symmetric mass ratio, spins, and so on. Here enter symmetric mass ratio, spin, and so on. Again, the symmetric mass ratio is dimensionless, so it can enter the coefficient as it is. The spin it has dimension, so what enters is spin divided by m to the 4, sorry, spin divided by m to the second, and spin divided by m to the second. All of these parameters, they gives kind of corrections to the shape of the waveform, whose main parameter is m chirp, because m chirp sets the scale of, sorry, I didn't define m chirp. This was m to the 5/3, which is there just for dimensional reason, because the power here is 11/3, f dot over f, sorry, f dot over f, here the power is 8/3, just because I put an f here. I put an f, so this is, yes, and the dependency is on eta times the mass to the 5/3. The mass to the 5/3 is dimension, is a question of dimension. The eta to the 1 is just the point of the ratio. This goes as eta squared, this goes as eta, so it has to go to the eta. So usually at leading order, you see that there is this combination. Eta to the 3/5 times mass, everything to the 5/3. So this is called m chirp to the 5/3. So this is the parameter that is crucial to build the waveform, but then you need all the other ones to give the corrections. And then, of course, this is just to build the waveform, the intrinsic part. Then you need all those projection angles to see what actually is hitting your detector. Ah, yes, and the distance, of course. So, yes, by the way, what we measure at the end is just the distance, is not the redshift. So at the end, we have zero information about the redshift, zero. Okay? So we measure only the distance. If you want to do cosmology, you need somebody else to tell you the redshift. And then you combine with the distance, and so you can do cosmology. But the dependent on the distance is trivial, no? It's just 1 over the distance. Whereas to build a waveform, you need all of these details.
Let's thank Ricardo again. We'll make after lunch we meet